Alright, this is going to be our second look at dynamics of differential equations, and here's the situation. Suppose that a water tank holds 100 gallons of water. A briny solution which contains 20 grams per gallon of salt enters the tank at a rate of 3 gallons per minute. At the same time, the solution is well mixed and the solution is pumped out at a rate of 3 gallons per minute. We're going to let S be the amount of salt in the tank, and given the two rates, it's hopefully obvious that the level in the tank is not going to change. So let's first get our differential equation. We have a statement here that says something about the rate. Right? This word tells us quite a bit. So if I say the rate of change of salt as a function of time, I should be able to extract that information from the differential equation, or the context. So let's look at the individual pieces. All right, a solution which contains 20 grams per gallon of salt enters the tank. So 20 grams per gallon of salt enters a tank at a rate of 3 gallons per minute, which means that we have 60 grams per minute coming in. And again, checking the units. This is grams per minute. And then, of course, at the same time, that means something else is going to happen here. The solution's well mixed and the solution is pumped out at a rate of 3 gallons per minute. Okay, so we need to remove some salt from this thing. And let's see here, how much salt is in there? We're going at 3 gallons per minute. If this thing's actually fixed at 100 gallons, so if I'm taking 3 gallons per minute divided by 100 gallons and then multiplying by the number of grams, that's also going to give me the number of grams per minute. And I have my differential equation. Now the underlying assumption here is that we're actually using a full tank. That's why I've got a 100 here. This could change if I was dealing with a tank that was only half full, that would be a 50. If it was a quarter full, that would be a 25, and so on and so forth. So let's look at the dynamics of this particular differential equation, and first we're going to find equilibria. So if I want to find an equilibrium, I'm going to set the rate equal to 0. So if I have 0 equals 60 minus 3 over 100 S, and I solve that for S, so that's 3 over 100 S equals 60, so S is equal to 60 times 100 over 3. Let's see here, 60 over 3 is 20, 20 times 100 is 2,000. So there's my equilibrium state. Right, now we're going to take this differential equation and actually figure out what the dynamics look like. So the differential equation again is ds dt equals 60 minus 3 over 100 S. The equilibrium is S equals 2,000 that we found before. So if we plot S versus ds dt, so this is S versus the rate, we should be able to figure out what this thing's going to look like. And I'm going to throw 2,000 out here. And let's just see what happens on the left and right side of 2,000. This is a reasonably simple differential equation in the fact that this right-hand side is actually just linear. So if I throw in something that's less than 2,000 in for S, so something like 0, I'm going to get a positive number out. So I'm going to be somewhere up here. So I can just kind of stick that in. I know it's going to have a negative slope because this thing right here is the slope of this right-hand side. And if I throw in something greater than 2,000, say like a billion, this thing will be negative. So I know that my dynamics look something like that. So if I look at the phase plane or the phase line diagram, this is S, here's 0, here's 2,000. I can examine what's going to happen here by saying, well, ds dt is positive here when the amount of salt is between 0 and 2,000. So that means I'm going to be moving to the right. And ds dt is negative here when I've got more than 2,000. So I'm going to be moving to the left, which means that my equilibrium point, 2,000, is stable. Last but not least, let's draw a slope field for this. So again, the differential equation we're interested in, ds dt equals 60 minus 3 over 100s. And the slope field is when I look at t versus s. And in my case, I know that at 2,000, something very particular happens. Right? I know that my slopes are 0 when I plug in 2,000. So all I really need to do is investigate what's going to happen below and above. Now, of course, from the previous frame in this video, we know that this is a stable equilibrium. So below, for example, if I choose to go at 1,000, my slopes are all going to be aiming towards 2,000. If I go even further below, it will be even steeper towards 2,000. You can plug in numbers and figure these exact values out. If I'm above, again, it's going to be facing towards 2,000. And even further above, it's going to be even steeper. So what this tells you is that your solution, if we say started at 0, my solution is going to come up and then come towards 2,000 and level off. If I start a little higher, I have slightly different behavior, but not drastically different. And if I start above, so let's say that this briny solution is actually very, very full of salts initially. It's going to drop because we're actually pumping more salt than we're pumping out more than we're pumping in. And if we start way above, we'll have these types of solutions. So the blue curves that you see here are what several sample solutions would look like. Notice I did not draw any with negative salt because in the physical context of the problem, it makes no sense.